Today I wanted to continue our discussion which we started in the last class on YODA's miracle algorithm. So we said that we don't want to choose all nodes in the stake pool to do the computation for the CIT. So we choose a small subset which we call an execution set. So the advantage of choosing a smaller subset is that fewer of them do the computation. So there are fewer transactions put on the blockchain. But at the same time, how do we know that what they are submitting is correct or not? If we chose the whole stake pool, we said that we could just go by the majority rule because the assumption is that majority of the nodes are honest. Here we can't be so sure because we are randomly choosing a subset from the stake pool. So majority might be Byzantine. So what we said is we are going to go in various rounds. And we said let's start with round 1, and we said that there could be, we look at what solutions were submitted, and this is saying the number of nodes which have submitted a particular solution. And since these are close to each other, we said we can't be sure, right? And so we are going to repeat this procedure till we have enough confidence about which one is correct. Okay, so there are various issues which we will have to discuss. So the first issue is when to terminate. So essentially after how many rounds? And the situation is a little bit tricky because the adversary could do a lot of mischief. So suppose that S2 is the correct answer, the adversary might submit many solutions. Let's say this is S3. So S1, so let's say that he submits several solutions. So he could submit several of these, and we'll have to, of course, when we do our math, we'll have to take this into account. He could submit any number of solutions. In fact, he could submit 10, 20 different solutions just to confuse anybody. Right? And so the solutions that he submits in different rounds may be different. So of course here I am showing that he submitted 3 solutions, but he can submit a different number of solutions and even totally different solutions in different rounds. So how are we going to deal with this? So we need to have the appropriate mathematics in order to actually handle this. And what we are going to use is something called hypothesis testing, which you may have come across in some other course. So this comes about in many different applications, for example, you can consider, let's say, a defense situation. Let's say there is an aeroplane, and you have some radar signal, right? So right, let's just say that there is an aircraft, right, and right, a military fighter jet, let's say, right, and you have a radar over here. So the radar is going to give some signal. Let's just call it R. And you have to decide whether there is a plane or not. So this, of course, has to be done all the time. I mean, you don't have a human being looking up into the sky. You just have some equipment, and it has to decide automatically, is there a plane or not. Okay, and depending on that, you would want to fire a missile or something like that, right? Of course, if it's a civilian application, you just need to know if there is a plane. It needs, whether it's, planes are going to collide and that sort of thing. So the thing is, how do we do it, right? I mean, and this decision could be critical because lives could be at stake. So we have to be able to do this correctly. And of course, you can imagine that if the radar signal is better in some way, maybe this plane is closer, so the radar signal is better, then you can more easily say whether there is a plane or not. Okay? But otherwise, normally what you have is this signal which is corrupted by noise, right? So maybe when you study hypothesis testing, you will look at something like this: signal plus noise, right? So this is from the aeroplane, and what the radar gets is the total amount of this, right? And if the signal is much stronger than the noise, then of course you can say more clearly, right? But how do we do the mathematics for this? And that's where hypothesis testing comes in. So hypothesis 1 says that that there is a plane, and H2 is that there is no plane. Okay, and suppose it's a defense situation, then of course we're talking about enemy planes, so we have to shoot down the plane, and here of course we do nothing. So there's a price to be paid if we if one hypothesis is true and we say that the other one is true. Okay, if H1 is true and we say that there is no plane, then we get bombed, right? And if we say that there is no plane when there is, okay, I mean, if we say that there is a plane and actually there is no plane, then we might fire off a rocket into the sky. I mean, of course, there is some monetary loss there, right? Anyway, so the wrong decision is costly. So how do we talk about this in terms of probability? So we want to talk probability that we say or guess. So basically we are going to look at the signal and we are going to say H1 is true, and in fact H2 is true. And this is called the false alarm. So this is the false alarm probability, PF. So we want to keep this false alarm low. We don't want people to panic and think that there's an enemy plane flying over when there isn't one. Also, we could say H2 when actually H1 is true. and this is called the miss probability. We missed that the plane was in the sky. So now ideally, in an ideal situation, you would want to keep both of these 0. You would want to have the false alarm 0 and the miss probability 0. But it's non-trivial to do that. I mean, it could be impossible to do it, given the amount of noise in what you're measuring as. Okay? It could be trivial to make one of them 0. And how would you do that? You would have to think. So suppose we wanted to make false alarm 0. One thing is, we could always say that H1 is true. Then we'd never have this situation of a false alarm. We'd always say that there is no plane, right? And so this would never happen. We would never say that there is a plane, so there would never be a false alarm. But then the problem is, our miss probability would shoot up, because even when H1 is true, we would keep saying that H2 is true. So this is the conditional probability, this particular notation. So we are saying that H1 is true conditioned when H2 is actually true. Okay. So how do we go about doing this? I mean, there seems to be a trade-off. We could very easily make one of them 0, but then the other probability shoots up. So in practice, what methodology we use is that we set some limits on both of them. Maybe we say, I don't want my false probability to go above some limit. I want it to be less than some threshold. And then I try to optimize the other one. So the user, which in our aerospace application is, let's say, the military. So the user specifies some bounds on PF and or PM, okay, and tries to optimize. So you could say that I want a bound on PF and then I minimize PM to as much as possible. And how do we do this? Well, it turns out that all particular hypothesis testing problems end up with something called a likelihood ratio. So the solution, it looks like the following. So I'm assuming, of course, there are only 2 hypotheses here, and I'm giving you what it would look like. So we would have the probability of R is my signal, conditioned that H1 is true, and we end up with this ratio R given H2 is true. So this is called the likelihood ratio. So this likelihood ratio we are going to compare to some threshold. And if it is larger than the threshold, then we say H1, and if it is less than the threshold, then we say H2. Okay. So this might, if you're seeing this for the first time, it may look a little bit odd. So these are the conditional probabilities. So what the user knows is, he knows what R is. He gets some signal, right? And he looks at these 2 conditional probability distributions and he says, for which of these hypotheses is that R more likely to occur? right? And if that R is more likely to occur when H1 is true, then of course I'm being pushed towards guessing that H1 is true, right, compared to H2, right? But maybe there's another signal which is more likely to be received when H2 is true, okay, in which case this ratio is going to be smaller, and then I'm going to prefer to guess H2. Right? So normally what you end up with is something like this. There is some threshold, so you look at this, you first, given what R is, you compute these two conditional probabilities, take the ratio. If the ratio is larger than the threshold, you say H1 is true, and otherwise you say H2 is true. So these are the guesses that you make. Okay. And pretty much most of the hypothesis testing would look like this in the case you have just two hypotheses, right? So of course when you choose depending on what you specify, what criterion you specify, you may end up looking at a different threshold. Suppose I say my false probability has to be less than 10 to the power of minus 3 and I minimize the miss probability, right? I end up with one threshold. But instead of 10 to the power of minus 3, I say I want it to be 10 to the power of minus 9, then this threshold would be different. But always the methodology, the way of saying whether H1 or H2 is true is this: you take the likelihood ratio and compare to a particular threshold. Okay. Okay, so T is determined based on the criteria specified. On the user specified criteria. So this is in case when you want to make a single decision, right, given a single signal R. The question is, how do we deal with our situation where we have multiple rounds? Okay, so in our case, our signal is essentially going to be the number of votes that we got for different solutions. Okay. And we are going to do this many times. Okay. So how are we going to deal with multiple rounds? So suppose the radar collects signals R1, R2 and so on up to Rn in certain time intervals. Okay. 1, 2 and so on up to n. Okay, so maybe there's a plane going by somewhere, and in the first 5 seconds you chose, you collected one signal, and in the next 5 seconds you chose another signal and so on. Now you want to detect in real time whether there's a plane or not. Okay, so I'm just numbering the intervals, I'm leaving out the units or whatever. So there is some signal collected here, R1, R2 and so on up to Rn. Now I want to make my decision as soon as possible. Right? So if it's very clear that there is an aircraft here, I want to fire off my missile right away. But maybe the aircraft is very far off, maybe it's like 300 kilometers away, right? So the signal is very faint, I can't be sure. And maybe the plane is coming closer, so I see a better signal over here, but I'm still not confident, right? And so I want to make the decision as soon as possible, but I don't want to make a wrong decision. Right, so in real time I'm getting these, and I have to do my hypothesis testing every time I get a newer and newer signal. So what we have is let's say some particular signal, okay, and so after n rounds, this is the signal. Let's just call it the total received signal, okay, which is aircraft signal plus the noise, we said. Okay, so this is what you receive, and this is just a vector of all of these, right? So we just put all of these together, and this gives us a vector. And as n keeps increasing, we want to try to make a decision, right? So initially we have just R1, which is just this, and R2, R superscript 2, 3, and so on. We collect more and more signal. And this whole procedure is called sequential hypothesis testing. So what we do is the following: we look at after a particular round n, what we do is we calculate the likelihood ratio and here this is the ratio. The probability of getting this received signal conditioned on H1 being true, and what we're going to do is we're going to look at two thresholds over here. So if the ratio is very high, I mean it's greater than T1, then we are going to say H1 is true. Okay, and then we stop the hypothesis testing. So let's say we terminate. And here too, suppose the threshold is suppose the ratio is very small for a particular signal, then probably H2 is true. So we say H2, and of course stop. So in this case, we would have fired off a missile, and here we don't worry at all, right? We say we are confident that there is no plane over there. So what if the ratio is between T1 and T2? Then we just continue, right? So it is between T2 and T1. Okay, so if the ratio is in between these two, then we collect data in the next round. Then we repeat the hypothesis testing after that. Okay, so here we would have R n plus 1, okay, which would go in over here. Okay, in the next round. Okay, so if you plot the likelihood ratio, with round number, suppose this is T1 and this is T2. In one case, suppose there is a plane, you may end up after one round somewhere here, right? And after 2 rounds it may be here, after 3 rounds. But maybe after the 4th round it goes up here. So we say that H1 is true. But maybe there was no plane, but again we start out, we are not sure. And maybe it's something like this. But let's say it goes below T2 here. So here we say H2 is true. So this is how the sequential hypothesis testing works. Right? And in practice, what you would do is you would take a log over here. Okay, so of course there are different reasons. So you can take a log on both sides. It doesn't change anything. It's just that instead of a ratio, you're going to have a difference. And also, of course, you're going to squeeze the range of these values, right? This range could be very high. If you take a log, you're dealing with smaller numbers. It also turns out that very often in this hypothesis testing, you deal with some sort of Gaussian distributions. So by taking a log, so Gaussian looks something like this. So you're familiar with the Gaussian distribution. If you take a log, you get rid of this e to the power of something. You just have this exponent. So effectively what we do is a log likelihood ratio and we are going to compare this to log T1, log T2 and so on, right? And of course if it's in between these two, then we repeat, we go to n plus 1. So what we have to consider now is how to find those thresholds. Okay, so this is all nice theoretically, but what are these probabilities and what are the thresholds? And in our case, it's not enough to look at 2 hypotheses. So what if there are more than 2 hypotheses? And of course, like I already mentioned, what are these probabilities? Okay, so this is what has to be looked at in any hypothesis testing problem. But of course, in our case, we are going to try to find the solution. It might be different in different hypothesis testing problems. But what we are going to look at is the mathematics for our particular problem. And our situation is actually much more trickier because you have an intelligent adversary. Normally in this hypothesis testing, you have just a signal, a real world signal plus some noise, right? There's a plane or something like that, and the physics decides what signal you actually receive. Whereas here there's an adversary, you can decide what the signal is going to be. You can vote for any solution and change the signal, right? So that is what we will describe next. So let me explain what we do in YODA. So first thing is that we are going to assume that the Byzantine fraction is actually F max in the state. And under this assumption, we are going to try to get this probability. Okay. So suppose there are, let's say, totally k different solutions submitted. So we want to find probability of Rn given Hk, okay, for all the hypotheses. So of course each HK will each hypothesis corresponds to a different solution. Okay, and so what is Rn really? And let's write that out formally. So suppose in round 1, these are the solutions. Okay. There are this many solutions, let's say, submitted, and the counts, the number of votes for each of these is C11, C21, and so on. Cn1. So effectively, my signal, you can say, in this particular round is just all of these put together. And of course, if we go on to different rounds, let's say round J, okay, so I'm going to use this second subscript for the round number. So Rn is just it's going to be all of these put together. Okay, up to a particular round. Okay, so all the votes in different rounds up to round, including round n, is R superscript n. Okay. So let's simplify it a little bit, and let's assume that the adversary has submitted only one wrong solution. So we have just two hypotheses totally. So consider the case where the adversary submits only one wrong solution. Okay. So we just have in round J, C1J is, let's say, the number of honest votes. So we're looking at round J. And C2J is the number of Byzantine nodes in ESJ, and we are assuming that the Byzantine nodes have submitted all their votes for S2. Right, so in theory, of course, they could be silent also. Only some of them, a subset of them, might vote for S2, but we are assuming all Byzantine nodes vote. So the question is, how many of these are we going to see? And if you think about it, you have a stake pool. And we are going to select a random subset. So how we select them and so on, we can discuss about later. But let's just think that for each of these, we flip a coin and we decide whether it's going to be in the execution set or not. Okay, so to construct, let's say to create the execution set in round J, let's say we choose any node in SP with probabilities of Q. And so the probability that a particular node is selected is Bernoulli. It's just a coin toss, right? And let's say probability node I is selected is let's say Bernoulli, and I'm going to represent this as a random variable Ni. Okay, so this Ni can be either 0 or 1, and 1 means it is selected. Okay. So what is C1J and what is C2J? Okay, so we are going to assume that So we are assuming that S1 is the correct solution. So what do we get? C1j is just equal to summation of I is equal to, so suppose the number of nodes in the stake pool is M, and let's say F is the fraction of Byzantine nodes. So essentially I am going to get a sum of these Bernoulli random variables. So 1 minus f is the fraction of honest nodes. Okay, so there are this many, and I am just going to put a superscript h to represent the honest nodes. And C2j is just a similar summation among the dishonest nodes, which I'll just call them B for Byzantine. Okay. So what is this? So it's a sum of Bernoulli random variables in both cases, right? And I'm going to approximate them as a Gaussian distribution. So is this approximation good or not? Well, we are summing up a number of independent random variables. Okay, so we are separating out the nodes into Byzantine and honest, and we are seeing how many of these honest nodes are selected. That is given by this, right? And C2j is given by the number of dishonest or Byzantine nodes selected, given by this sum. So if this number is large enough, then it's well approximated by a Gaussian distribution, but otherwise not, right? So, but we are for the time being assuming that it is Gaussian. So what would it give us? Cij is a Gaussian distribution. And so the mean is going to be given by this, and the variance is given by this. So Q is the probability of choosing a particular node. It's a small probability. If you want a smaller execution set, you need to set Q smaller. Right? So this is the mean, and this is the variance. So I'll just call this mu h, and this I'm going to call nu h square. Okay. And similarly, C2j is going to be Gaussian distribution with just f replaced by 1 minus f. 1 minus f replaced by f. And I'm going to call this nu b square, and this is mu b. So what is our log likelihood ratio? So I'm going to define L1n is just log probability that Rn condition on H1 minus log PR of Rn condition on H2. Okay. So what is H1? Is saying that S1 is true, S1 is the correct solution, and H2 is saying that S2 is correct. So I don't know which one is correct, right? Because I don't know who's honest and who's dishonest. Okay. So the question is, if S1 is if S1 is the correct solution, then what's the probability that I see this many number of votes for S1 and S2 in the different rounds? Okay. And so on. If S2 is correct, then what's the probability of seeing this many votes? Right? That's what these probabilities mean. And this turns out to be this. C1j minus mu h square divided by 2 nu h square. So this is where taking the logs helps. So the Gaussian exponent comes out. Plus okay, so this whole thing has to be summed up. Okay, so this comes from the H2 hypothesis, these two, and this first term results in these two. So what is changing from here? Well, here we are assuming that S2 is the correct solution, so we have to subtract out mu h, right? And here, of course, if S1 is true, then these votes are coming from the Byzantine node. So this is sort of the intuition why you go from mu b to mu h and so on. And this simplifies nicely to give us this formula. And so we are assuming that f is equal to f max. So we end up with 1 minus f max minus f max by 1 minus f max times f max C1j square minus C2j square. Right? Okay, so based on a Gaussian assumption, we came up with a very nice simplified formula. This is just a constant, and we just take the difference of the squares of the counts of votes in each round. Okay, so this square comes up because of the Gaussian distribution. You have e to the power of minus x square, right? And we end up with this over here. Okay. So a very clean sort of formula for the log likelihood ratio. And remember that beta is the user specified probability of making the wrong decision. Okay, so what I mean here is that the user ends up saying that the wrong solution was the correct one. Okay, so that is a probability that we give, and so if L1 of n is greater than log 1 minus beta by beta, then we say S1 is the solution. Okay. And if the second log likelihood ratio then we say that S2 is the solution. And what is this L2n? Well, L2n is the log it's just going to, in this particular case, it is going to be minus of L1 of n, because we just have two hypotheses. Okay. This is anyway going to be log probability of Rn condition on H2 minus log probability of Rn condition on H1. Okay, it's just a negative of L1n in this case. When we have only two hypotheses. Okay, so fine. So we have worked out everything when the attacker only submits one solution, one wrong solution. All the time he votes for that particular solution in all the rounds, right? And in that particular, and we are also saying that his fraction is actually equal to the worst case F max. So we designed for the worst case, and in that case, we end up with this number of rounds, expected number of rounds to terminate is 1 minus beta times log 1 minus beta by beta plus beta times log beta by 1 minus beta, and here we have mu h minus mu b square plus nu h square minus nu b square. So this the calculations, of course, and where we get them and so on are given in the paper. So it turns out that hypothesis testing is a very old field. It's almost 100 years old, right? After the First World War and so on, whenever radar came up, they had to do all this analysis, right? And this theory is sort of very well developed and it's old. But what is new in this paper is that we have posed the problem as a hypothesis testing problem and made that connection, right? And beyond that also, like we'll see in a short while, that it turns out that it's not a traditional hypothesis testing problem where you have signal and noise. Here you have an intelligent adversary. So right now we've simplified things by saying that there are just two two solutions submitted, one wrong and one correct, but he could submit a number of solutions and we'd have to deal with that. Okay, so that's also where some innovation comes. Okay. So what we have shown here is an optimal solution. So in the sense that we are trying to minimize the expected number of rounds, okay, in order to meet the certain probability beta. Okay, so we are given beta. You want to minimize expected rounds to terminate. And assuming Gaussian and so on, what we have shown above is actually optimal. So assuming that the Gaussian distribution is indeed correct, right? But that is true only if your execution set is large enough, where we can actually use the central limit theorem to say that the sum of those Bernoulli random variables is indeed Gaussian. Okay. Okay, so this is an optimal solution assuming Gaussian given beta, and we have to minimize this, and we are also assuming that f is equal to f max. Okay, and adversary submits the wrong solution. Let's say the same wrong solution always. Okay, so this is what we are optimal in the sense. So conditioned on beta being given as the probability of us making a mistake, and assuming the adversary submits the same wrong solution in all rounds, and f is equal to f max, and our Gaussian distribution is exact, then actually these thresholds which I have shown over here, okay, so the thresholds that we've ended up with look like this, right? So what happens in practice is that we collect R superscript 1, and maybe neither of these log likelihood is actually greater than the threshold considered, because of which we don't terminate, we go to the next round and so on, and we wait till only one of them crosses the threshold, and then we terminate, right? And we say that particular, whichever likelihood crosses the threshold, we say that particular solution is the correct one. Okay, so we'll discuss what happens when some of these conditions don't hold, right? So we have designed it for this worst case, f is equal to f max, but the question is what if f is less than f max, what happens? And what we would like to see is that we terminate in fewer number of rounds. And also we have to look at the case when the number of solutions submitted by the adversary is not a single one. What if he submits more than one solution? Right, so that we'll discuss in the next lecture.